Hello everyone, welcome back to our channel. Let's discuss the next topic, that is coupling constant. In the previous class we had a discussion on spin-spin coupling and a multiplicity of NMR signal, right? Whenever we have the non-equivalent sets of protons, then what happens? The coupling phenomena takes place between those protons and it can leads to the splitting of the signal. So we have seen the hypothetical molecule. In the hypothetical molecule we are having two non-equivalent sets of protons. These two non-equivalent sets of protons are neighboringhood in nature. That's why HA is influenced by the spin of the HB and HB is influenced by the spin of HA. Thereby we will get two lines for HA and two lines for HB. This is one signal, this is another signal. So whenever we have two lines, three lines, four lines, already we know that singlet, doublet, triplet, like that we had a discussion, right? If you see this one, we have two lines in the signal. It means it is a doublet or not. In case of the doublet, the intensity ratio of signal is 1:1 according to the Pascal triangle. Okay, so if you observe this one, we have two lines. So in between the two lines, we have some space or not. So the distance between the lines in an NMR signal is commonly called as coupling constant. The coupling constant is represented by the letter J. See the definition? Separation or the distance between adjacent lines in a NMR signal is commonly called as coupling constant. For coupled protons, coupling constants are same. In a given NMR spectrum, from coupling constant, possible to identify neighboringhood protons. This is very important. What is the main use of the coupling constant? We can easily identify the neighboringhood sets of protons. So whenever the protons which are in coupling in the neighboringhood pattern, we can easily identify. Okay, the units are what? Hertz. Already we had a discussion related to chemical shift. The chemical shift value in the hedges is dependent on the strength of the external magnetic field and instrument frequency. That's why we have introduced the delta scale and tau scale. But in case of the coupling constant, it is independent in nature. It is not going to dependent on the strength of the external magnetic field or instrument frequency. Okay, so it is always independent in nature. What is the main use? We can easily identify neighboringhood protons by using the coupling constants. Okay, suppose assume that this is the hypothetical molecule. In the hypothetical molecule we are having two non-equivalent sets of protons. Already we know that H1 is influenced by the spin of the HB, then HB is influenced by the spin of the HA. So what is the meaning? Whatever the J value we have for the HA, then the J value for the HB both are going to be same. So whenever we have the same coupling constant for different protons, then we can say that those protons are adjacent to each other. Okay, so this is coupling constant. Let's see what kind of coupling is possible between different spin active nucleus. Here it is the proton nucleus, that's why we will talk about the proton couplings only. We all know that geminal protons means the protons which are attached to the same carbon, commonly called as geminal protons. If the coupling takes place between the geminal protons, then the coupling is commonly called as geminal coupling. Very easy or not? Okay, the coupling is takes place between the geminal protons. Assume that these two hydrogens are non-equivalent in nature. Okay. If these two are equivalent in nature, coupling possible, but there is no splitting in the signal. Already we had a discussion. Whenever the same kind of nucleus will be in the coupling, that will not give any kind of this spin-spin coupling or splitting phenomena. That's why whenever you want to observe the splitting of the signal, we need to have what? Non-equivalent sets of protons. So when will we observe these two protons are going to become non-equivalent? The best example is styrene. See this one, if this carbon is connected to pi bond, and if we have one single bond here like this, and this one is going to attach to the benzene ring system. Now see, here we have one another proton. Okay, this is phenyl ring, hydrogen. In this kind of situation, what happens? These two hydrogens will become non-equivalent. Okay, then coupling takes place between these two, and these are going to give splitting of the signal. Doublet by doublet. Multiplicity n plus 1 rule. Okay. Vicinal couplings. Vicinal coupling means coupling between the vicinal protons. Vicinal protons are what? The protons which are present on the adjacent carbons. Adjacent carbons, if the protons are present, that coupling is commonly called as vicinal coupling. If the splitting takes place between these two, then the coupling is commonly called as vicinal coupling. This is the best example, the hypothetical molecule. In this hypothetical molecule, how we are observing these two protons? These two are present on the adjacent carbons or not? That's why this coupling is an example of vicinal type of coupling. Okay. Next, allylic coupling. The name itself indicates allylic. The coupling between allylic carbon and carbon attached to the pi bond. See this one, pi bond is main or not? If the coupling takes place between these two, then the coupling is commonly called as allylic coupling. Next, homoallylic coupling. Allylic with one carbon. See this. This carbon is allylic carbon. So the next carbon is what? Homoallylic carbon. If the coupling takes place between the homoallylic hydrogen and hydrogen of the unsaturation, is commonly called as homoallylic coupling. Next type coupling, cis-trans coupling. Already we know that cis-trans phenomena observed in alkenes. The coupling between cis protons, the coupling between trans protons, these should be non-equivalent in nature, then only we will observe the splitting of the signal. Okay. Next, aromatic couplings. Already we know that if we have some substitution at benzene, then we will observe these kind of couplings. See this, this is X group, this is Y group. These two protons are ortho to each other or not? Then such type of coupling is commonly called as ortho coupling, meta coupling, para coupling. Okay. Virtual couplings. Generally, we are observing the coupling between the adjacent carbons, right? If the coupling is takes place between the non-adjacent neighboring good protons, it means, see this, CH3 and this CH2 both are non-adjacent to each other or not? If the coupling is possible between these two protons and these three protons, such type of coupling is commonly called as virtual coupling. If the coupling is takes place between this CH3 and this CH2, this CH3 and this CH2, like that, this CH2 and this CH2. Okay, such type of couplings are called virtual couplings. All these kinds of couplings are divided into two portions. What are those? Short range couplings and long range couplings. Long range couplings are weak couplings. Short range couplings are strong couplings. Why? Because whatever the coupling which we are observing in all these cases, all these couplings are possible through the bonds only. through the bonds, first bond, second bond, third bond, and fourth bond. Already we know that if the distance is increasing, number of bonds are increasing, the coupling strength will be decreased. Right? That's why based on the number of bonds, the people are consider these kind of couplings in two categories: short range and long range. Short range couplings are stronger in nature, long range couplings are weaker in nature. So in each and every kind of the coupling we are observing, coupling constant or not. Remember that the coupling must be possible between the non-equivalent sets of protons. Then only signal splitting takes place. We will observe coupling constant. Coupling constant means what? Whatever the signal that is subjected to the splitting pattern, because of that reason you will get different lines. The distance between the different lines in the signal is commonly called as coupling constant. Okay, so these are the examples of the short range couplings. These are the examples of long range couplings. See this, with increasing in number of intervening covalent bonds between the coupled protons, the strength of the coupling decreases, thereby J value is going to decrease. Okay, here we have one more concept: homonuclear and heteronuclear couplings. The name itself indicates homo means similar kind, hetero means different kind. So, till now what we are observing? Coupling between the protons or not. Every time whatever the coupling may be, it may be a geminal coupling, vicinal coupling, allylic coupling, homoallylic, whatever it may be, in all these cases we have considered hydrogen only or not. But those hydrogens are non-equivalent in nature, but nucleus is same, no? Such type of couplings are commonly called as homonuclear couplings. The coupling takes place between similar kind, same kind of the nucleus is commonly called as homonuclear coupling. If the coupling is possible between two different spin active nucleus, then such type of couplings are called as heteronuclear couplings. Okay, so in the next unit we are going to have a discussion on the C13 NMR spectroscopy. In the C13 NMR we are going to observe the coupling between C13 nucleus and proton nucleus. Such type of coupling is an example of heteronuclear coupling, right? So whatever the coupling we have, in every case we are going to have coupling constant or not. So how can we have, how much the constant is going to, right? Geminal coupling means coupling between the geminal protons. If you see the distance 1 2, so two bonds are there or not. That's why it is represented as J2, J power x. X is number of intervening bonds. Okay, this value is 10 to 18 Hz. In case of vicinal, number of intervening bonds 1 2 3. That's why this is J3 or J vicinal. Once the number of bonds increases, the coupling strength decreases, thereby what happens? The coupling constant value will be decreased. The vicinal coupling constants are inversely proportional to the electronegativity of the atom, bond angle and bond length. It means bond length increasing means what? J vicinal decreasing. Bond angle increasing, decreasing. Electronegativity of the atom increasing, decreasing. Generally, these vicinal couplings are observed in most of the cyclic compounds. That's why we have an equation called as Corpus equation. J vicinal equal to A plus B cos theta plus C cos 2 theta. In case of the conformational isomerism, we are having the concept of conformers or not. There we are going to use the dihedral angle theta. This theta is the dihedral angle. So based on the dihedral angle, we are going to get the different values. In case of vicinal, eclipsed form, Gaussian form, staggered form, anti-form, we have different forms or not. So in order to identify the vicinal coupling constants in such type of cases, we are going to observe these kind of things. Okay, the ABC values are fixed. Okay, so this is the graph which we have according to the corpus. You can remember this one. Generally, three conditions, na? 3 to 4 condition. One is the 0 dihedral angle, 60 dihedral angle, 90 dihedral angle, and 180 dihedral angle. This is the situation we are. Axial equatorial. Here also we are going to observe. Next, allylic coupling constants. 4 bonds. 1, 2, 3, 4. That's why J4. Number of bonds increases means strength decreases. Homoallylic means 5 bonds means J5. Strength decreases, value decreases. Cis trans coupling. In case of the trans couplings, J value more. Cis coupling, J value less. Why? Because due to steric crowding. Okay, steric strain. Strength of the coupling is decreases, thereby J value decreases. This is one of the best example. Cis cinnamic acid and trans cinnamic acid. The coupling between these two are chemically non-equivalent or not. That's why coupling phenomena takes place. Because of the coupling, we are going to get the signal. This proton will give doublet to this one. This proton will give doublet to this one. So two doublets we can get. So according to that, we are going to have coupling constant value. So aromatic coupling, ortho, meta, para. If you see ortho, 3 bonds are not. That's why value more. Here the number of bonds increasing, coupling constant decreasing. 1, 2, 3, 4, 5. 1, 2, 3, 4. That's why ortho coupling constants are higher than meta than para. How can we represent the NMR spectra? Generally, how we are going to observe the NMR spectra of different kinds of the chemical compounds? In this way, we are observing 0 means this indicates chemical shift value. This axis is the frequency axis. Chemical shift value from the right to left. Okay, this is intensity axis. Already we know that the intensity for each and every kind of the signal, singlet, doublet, triplet, already discussed in the last lecture, right? So if you see the spectra, if your compound is having doublet, this is doublet, above that one we are having this kind of stepped curve. In every case, we are going to get this kind of stepped curves. The stepped curves are commonly called as integrations. What is the name? Integrations. Remember, integration. So, around the 0, that portion is called as a shielding region. Around the 20, that region is called as a de-shielding region. De-shielding region is commonly called as a downfield region. Okay, shielding region is commonly called as upfield region. Shielding region is commonly called as upfield. Most of the students are going to get the confused. Okay, do not get confusion related to the upfield and downfield. Upfield means shielding, downfield means de-shielding. Already we know that de-shielding means chemical shift values are higher. Shielding means chemical shift values are lower. Simple. Okay. So what is the use of this stepped curve? What is the use of this integration? Suppose if you take the height of the height of the curve is going to give the ratio of protons which are present in the signal. It is going to give what? Ratio. If you know the height of the stepped curve, we can identify the number of protons which are present in the molecules. Okay, that is the importance. From this we are going to get the ratio of protons. Okay, height of peak in NMR signal proportional to the number of protons contributed in the signal. Indirectly, what we are going to get? The number of protons. Okay, so these are some of the examples. Here J values are there. What is the use of the J value? The J value is used to identify the number of neighboring hood protons. See this one. We have a molecule that is ethyl chloride. Assume that you don't know this molecule. You have data like this: 3 protons triplet, 2 protons quadrat. What it is? J equal to same 7. If the J value is same, that indicates these protons are adjacent to each other. Simply remember like this: whenever the J value is same, the corresponding protons are adjacent to each other. Okay, see this: 3 protons means if we attach to the carbon, what happens? CH3. 2 protons, if we attach to the carbon, how can we write? CH2. So CH3, CH2. These two are adjacent to each other. Okay. So in this way we can identify. Already we discussed that in case of the mono-substituted benzene, we are getting 3 types of protons: orthoprotons, orthoprotons, metaprotons, and paraprotons. Here what the people are saying: whenever you have weak electron releasing groups or weak electron withdrawing groups, the instrument cannot recognize ortho, meta, paraprotons separately. They will consider all 5 protons in same environment. So whenever we have weak donating group or weak withdrawing group, you need to get only one signal related to the benzene nucleus containing 5 protons. So all the 5 protons will appear as one signal. Okay. So here these are some of the examples, so you can see the examples. At the ending of the chapter, we will have brief discussion about the problem solving related to the NMR. Okay. So in the meantime, you can take these examples and you can try. Next, W type couplings. The long range couplings on the rigid saturated molecules are commonly called as W coupling. What is the name? Long range couplings on the rigid molecules are what? Bridged cyclic compounds are not. So this kind of situation we are going to observe in bridged cyclic compounds, nor Bornene systems in generally we can say that. See, if you see this situation, it is like W shape or not? If you do like this. So you have a proton here and we have a proton here. If the coupling is takes place between these two protons, then such type of couplings are commonly called as W couplings. Generally, we know that the trans coupling constants are higher than the cis coupling constants as for the general situation. But in case of the three-membered rings, because of the higher ring strain, what we are observing, trans coupling constants are going to be lesser than comparing with the cis coupling constants. Okay, this is all about coupling constant and types of coupling possible in different chemical systems with proton. Okay, so in the next class we are going to discuss about the first order and non first order proton NMR. Okay, thank you very much.